3.2 deals with Rolle's theorem, and Rolle's theorem is an application of derivatives. So let's take a little preview of Rolle's theorem first. So what Rolle's theorem says is that if we have some function, so suppose we have this function here on a closed interval. So let's close our interval. So that's intervals from a to b. If our function is continuous, so first of all, we have to be continuous on a to b. And if it's differentiable on a to b. And one other thing, if the endpoints are at the same height. So if the endpoints are at that same height. So my drawing is off a little bit here, but I'm going to fudge just a little. So let's suppose on the left side and the right side of our closed interval that we're at the same y value. Well, in order to get from here to here, if we go in a straight line, notice that the slope of that straight line would be 0. Notice if we go up, then to get back down to the same height, we would go through a critical point. So we would have a slope of 0 there. And you might say, well, what if we had one of those little sharp peaks? Well, that's covered by differentiability. If we had a sharp peak, it would not be differentiable. So since the derivative does exist everywhere inside our interval, if we go up and come back down, there must be a place where our slope is 0. Or if we go down and then come back up, our graph didn't. But imagine if we were to go down, then we would have to come back up if we were going to be at the same height. Then somewhere in between those 2 points, not necessarily halfway, but somewhere in between there, we would have a slope of 0. So Rolle's theorem is just dealing with if we have a continuous smooth curve that's differentiable, if we're at the same height on both edges of our interval, then whether we go straight across, whether we go up, then down, down, then up, somewhere in between there, at least one point, there will be a slope of 0. There will be somewhere where our first derivative is 0. Always. So let's look at a few problems. And to begin with, we're asked, does Rolle's theorem apply? So for it to apply, we have to meet all those criteria. So first of all, is it continuous? Is this function continuous? Well, yes, it's a polynomial, so it's never going to be undefined. Is it differentiable? Well, how do we find out if it's differentiable? We take the derivative. That's minus 2x plus 3. And it's never undefined, so it's differentiable. And then the third criteria is that f of 0 and f of 3 have to be equal. We have to be at the same y value on each end of our interval. So if we plug a 0 in for our function, 0 squared is 0. 3 times 0 is 0. So f of 0 is 0. So when we substitute a 3 in, we have to get 0, or Rolle's theorem does not apply. It only applies when both ends are at the same height. So if we put in a 3, we get minus 3 squared is 9. 3 times 3 is 9, and that makes 0, so that's true. So Rolle's theorem does apply. So once we figure out that Rolle's theorem does apply, we want to find out where inside our interval does our slope equal 0, or our derivative equal 0. So we're going to take our first derivative, set it equal to 0, and solve for x. So if we add 2x to both sides, we get 3 equals 2x. And then when we divide, we get a critical point of 3/2. And yes, 3/2 is in our interval. So this is the point that's guaranteed by Rolle's theorem. This is the point inside our interval that has a slope of 0. All right, let's look. Here, they want us to find out, does Rolle's theorem apply? So let's check for continuity. For this function, notice x cannot be 3. Now, if 3 is not inside our interval, that's not a problem. But 3 is in our interval. So we're not continuous. So we don't meet the requirement of being continuous. Once we take the derivative of this, we would have to use the quotient rule. So we would have u prime v minus u v prime. And on bottom, we would have x minus 3 squared. Notice this function is not differentiable when x is 3. So that value, if that were not inside our interval, that would not be a big deal because Rolle's theorem is only asking about differentiability inside the interval. But this derivative is undefined at 3, so it's not differentiable everywhere in our interval. Now we can check to see if the end values are the same. But we already know that Rolle's theorem does not apply. So the only reason I'm doing this is on homework, it's going to ask you to check off for which reasons is Rolle's theorem not going to be applicable. So it's not continuous, it's not differentiable. So we know it doesn't apply. Let's see if this one would also disqualify. If we substitute a negative 8 into the function, negative 8 squared, that's negative 8 times negative 8, minus 64 over negative 11, that's going to be 0. 0 over negative 11. If we put in 8, we get 8 squared minus 64 over 5, that's also 0. So that criteria is met, but even if one of the other ones fails, then Rolle's theorem is not applicable, or it does not apply. So we don't even look for a point inside our interval for which our slope is 0. There could be one, but Rolle's theorem doesn't say anything about it when these criteria are not met. Sometimes there will be a place where our derivative is 0 in the interval. Sometimes there won't, if Rolle's theorem does not apply. But if Rolle's theorem applies, there will always be one. Now this question, when you first read it, you might be like, how does this have anything to do with Rolle's theorem? But let's look at what we're being asked. We're told that the height of a ball that starts out at 5 feet and is thrown vertically at 48 feet per second can be modeled by this equation. So if we were to graph this function, time would be in the horizontal direction. F, which stands for its height, is in the y direction. So notice when time is 0, we would be at 5, and the ball would go up. This is being thrown upward, and at some point it's probably going to come down. So they want us to verify that when t is 1 and when t is 2, that they're at the same height. So how do we do that? Well, we plug them in. So if we plug in 1, 1 squared is 1, times negative 16 is negative 16. 48 minus 16, that's 32, plus 5 is 37. So when t is 1, when it's been going for 1 second, it's at a height of 37. Now if we plug in a 2, we get negative 16 times 2 squared plus 48 times 2 plus 5. So 2 squared is 4 times 16, that's negative 64, plus 96 plus 5. Well, 96 minus 64 is 32, plus 5 is 37. So after 1 second, it's at a height of 37 feet. And after 2 seconds, it's at a height of 37 feet. Now, if it's a ball being thrown up in the air, it's not just going to sit at 37 feet for a second or 2 seconds or however long. So why is it at the same height at 1 second and in 2 seconds? Well, that's because it's at a height of 37 feet when it's going up. And then when it starts coming back down, it's also at a height of 37 feet at some point. So in between 1 second and 2 seconds, it reached the maximum height and then it started coming back down. So that means that somewhere in between there, since this function is continuous, and since it's a smooth curve, it's differentiable, the endpoints are at the same height, so those are the three criteria of Rolle's theorem. Same height on both sides, smooth curve, continuous, so Rolle's theorem applies. So as a result, there's got to be some point in between there such that the slope is 0. So to find that point, and part B just asked, what does Rolle's theorem say? To find that point, we take the derivative. And what does the derivative of position tell us? Well, the derivative of position is velocity. If F tells us our height, then when we take the derivative, that's telling us the change in height, how fast the height changes. Well, if you're measuring how quickly a distance or a position changes, that's velocity. So when we take the derivative, we bring the 2 down, so that's going to be negative 32t. The derivative of the 48t is 48 plus 0. So that's our velocity function. So our velocity is going to be 0 at the peak. The derivative tells us slope, but it also tells us velocity here. So we want to know, well, when during the ball's flight is velocity 0? So we set, we don't put 0 in for t, we're trying to find t when velocity for our first derivative is 0. So take our first derivative, our velocity function, set it equal to 0. We could add 32t to both sides. If we divide both sides by 32, we get t is 1.5 seconds. T equals 1.5 seconds. So that's guaranteed by Rolle's theorem. Since we are at the same height on both edges, then somewhere in between there, we had to start coming back down. And at that moment when we turned around, we have a horizontal tangent line, which in this case represents velocity.